Have you ever paused to consider the magic in your pocket? That sleek smartphone is more than just glass and plastic. It's packed with tiny, almost invisible components. We call them rare earth minerals. Without them, the vibrant screen and powerful magnets in your headphones wouldn't exist. These elements are the unseen architects shaping our modern world, essential for gadgets, green energy, and advanced defense systems. 17 elements with unique properties. From electric cars to wind turbines, rare earths are there. What exactly are these rare earth elements, or REEs as scientists like to call them? The name itself can be a bit misleading. You might imagine them being scarcer than gold or platinum, but that's not entirely true for many of them. Cerium, for example, one of the 17 rare earths, is actually as abundant in the Earth's crust as copper. So why the rare label? It comes down to a few key factors. Firstly, they are rarely found in concentrations high enough to make mining them economically viable. They are often widely dispersed. Rare earth elements are similar. They are often found mixed together with other minerals, including radioactive ones like thorium and uranium. This makes separating them a complex and costly chemical process. The group includes the 15 lanthanide elements, plus scandium and yttrium, which tend to occur in the same ore deposits and exhibit similar chemical properties. Each of these elements has unique quantum mechanical properties that make them indispensable. For instance, neodymium and praseodymium are crucial for making the world's strongest permanent magnets. Europium and terbium are vital for creating the vibrant red and green colors in your television screens and LED lighting. Understanding this nuance is key to grasping why nations are so keen to secure a stable supply of these remarkable, if somewhat misnamed, elements. Let's zoom in on how these elements touch your daily life. That smartphone we talked about? It's a treasure trove of rare earths. Neodymium magnets make the tiny speakers and vibration motors powerful, yet compact. Lanthanum helps create the high-quality glass in your camera lens, ensuring those crisp, clear photos. Europium and terbium contribute to the brilliant colors on your display, making your videos and games pop with life. Without these elements, your phone would be clunkier, less efficient, and far less dazzling. But it's not just phones. Hard disk drives, the workhorses of data storage in many computers and data centers, rely on rare earth magnets in their read-write heads for precision and speed. Even medical technology like MRI machines uses massive superconducting magnets often cooled with the help of helium, but the imaging contrast agents can involve gadolinium, another rare earth, to help doctors see inside the human body with incredible detail. Jet fighter engines, missile guidance systems, drone technology, and sophisticated radar and sonar systems all depend heavily on the unique properties of these elements. For example, samarium cobalt magnets retain their magnetic strength at very high temperatures, making them ideal for precision-guided munitions and aerospace applications. Yttrium is used in laser targeting systems. The demand for these capabilities is only growing as our world becomes more technologically advanced. Now let's turn our gaze to one of the most significant challenges of our time: climate change, and the transition to green energy. Here too, rare earth minerals play a starring, if somewhat paradoxical, role. Many of the technologies we herald as saviors of our planet, the very tools designed to wean us off fossil fuels, are incredibly dependent on these special elements. Consider wind turbines, those majestic giants spinning silently to capture the wind's energy. The most efficient, direct-drive wind turbines use powerful, permanent magnets, made with neodymium and dysprosium to convert wind power into electricity. Electric vehicles, or EVs, are another cornerstone of the green revolution. They promise cleaner air in our cities and a reduction in greenhouse gas emissions, but the powerful, lightweight electric motors that propel these vehicles rely heavily on rare earth magnets, particularly those containing neodymium, praseodymium, and dysprosium. The batteries in many EVs also utilize various critical minerals, though rare earths are more prominent in the motors. As the world shifts towards electrifying transportation, the demand for these specific rare earths is projected to skyrocket, creating immense pressure on supply chains. The quest for a greener future is driving up demand for minerals whose extraction and processing can be anything but green. Section 5. The Global Hand: Who controls these elements? So, if these elements are so vital for everything from our gadgets to green tech to national defense, who actually controls their supply? This is where the story takes a sharp geopolitical turn. For many years, one nation has overwhelmingly dominated the global production of rare earth elements: China. It's estimated that China controls a very significant portion of the world's mined rare earths, and an even larger share of the complex refining and processing capabilities. This isn't an accident of geology alone, it's the result of decades of strategic industrial policy and investment. Historically, the United States was a major producer of rare earths, particularly from the Mountain Pass mine in California. However, due to rising environmental concerns, lower labor costs elsewhere, and complex economics, much of this production shifted overseas, primarily to China, starting in the late 20th century. This concentration of supply in a single country creates vulnerabilities for the rest of the world. Section 6. Whispers of conflict, rare earths in geopolitics. The strategic importance of rare earth elements hasn't just been a theoretical concern, it has already manifested in real-world geopolitical tensions. One of the most cited examples occurred in 2010, following a maritime incident near the Senkaku Diaoyu Islands, disputed territories claimed by both Japan and China. China reportedly halted shipments of rare earths to Japan. Japan's high-tech industries are heavily reliant on these materials for manufacturing everything from hybrid cars to electronics. This unofficial embargo caused significant alarm in Japan and sent prices of rare earths soaring globally. This incident served as a stark wake-up call for many industrialized nations. It highlighted the potential for rare earth supplies to be used as a tool of political leverage or economic coercion. The weaponization of rare earths, as some analysts termed it, became a tangible threat, prompting urgent discussions about resource security and the need for alternative sources. Section 7. The Earth's heavy toll, mining's true cost. While rare earth elements are crucial for our technological progress and even for some of our green ambitions, their extraction from the Earth comes at a significant environmental price. Mining any material involves disrupting landscapes, but rare earth mining can be particularly challenging. As we discussed, these elements are often found in low concentrations, meaning vast amounts of ore must be dug up, crushed, and processed to yield even small quantities of the desired minerals. This process itself is energy-intensive and generates enormous volumes of waste rock and tailings. The ores containing rare earths are frequently mixed with radioactive elements like thorium and uranium. Section 8. Refining the future, a chemical conundrum. Extracting the ore from the ground is only the first step in a long and complicated journey for rare earth elements. The next critical phase is refining, separating the individual rare earth elements from each other and purifying them to the high standards required by modern industry. This is an incredibly complex chemical undertaking. Remember, the 17 rare earth elements have very similar chemical properties, which is why they are often found together in nature. But this similarity also makes them extraordinarily difficult to separate from one another. The refining process typically involves a series of solvent extraction and ion exchange techniques, repeated hundreds or even thousands of times. This process consumes large amounts of energy and utilizes a cocktail of chemicals, including acids, bases, and organic solvents. Section 9. Beyond the horizon, seeking sustainable solutions. So, faced with geopolitical tensions, environmental concerns, and ever-growing demand, what does the future hold for rare earth minerals? The path forward requires a multi-pronged approach, focusing on diversification, innovation, and sustainability. One key trend is the global effort to diversify supply chains. Nations are actively supporting exploration for new rare earth deposits within their own borders or in friendly countries. They are also investing in reviving old mines and developing new ones, with a stronger emphasis on adhering to modern environmental standards from the outset. Another crucial avenue is innovation in how we use and find alternatives to rare earths. Scientists and engineers are working hard to design technologies that require fewer of these critical elements, or can substitute them with more abundant, less problematic materials. For example, research is underway to develop powerful magnets with reduced neodymium or dysprosium content, or even magnets that use no rare earths at all. Similarly, efforts are being made to improve the efficiency of existing technologies to get more performance from smaller amounts of these precious resources. Recycling is also a vital piece of the puzzle.